Now this is the last lecture of the course, and I'm going to tell you about big data analytics. So I'm basically going to give you an overview of this and the support that relational databases must have for big data analytics, and I'm going to talk about MapReduce and Hadoop. Although I have several slides on functional programming on which MapReduce is based. So map and reduce actually are functions taken from functional programming language. So I have given some background about functional programming in the presentation, and one implementation of functional programming called as Gopher. So that I've just put for the sake of completeness, and in this lecture I'm not going to actually talk about functional programming in a lot of detail. So if you are interested, you can go through those slides which talk about functional programming in detail, and also a very popular implementation, a simple and popular implementation called as Gopher. So the topics that are listed for today are big data analytics and extended RDBMS architecture, which I've taken mainly from the Kimball's Data Warehouse Toolkit book, the last chapter on big data analytics. And I'm going to talk about MapReduce and Hadoop. So big data analytics, like if you want to understand the challenges posed by big data analytics, I think this is a very nice way to understand this. I don't recall where I read this, but it is stuck in my mind. So it is like a mountain of data that you have to climb. The height of the mountain keeps increasing every day, and you have to climb it in less time than yesterday. So this is the challenge. So this is the kind of challenge that big data throws at us, right? So as you know, that the amount of data in the world is growing at an unprecedented rate, and it keeps coming to you, and at the same time the need for real-time analysis is also increasing. So nobody wants to wait for the analysis, right? So everybody wants to do real-time analysis, right? So that has posed this kind of a challenge to all of us, right? And has forced us to go back. So what big data has done is that it has forced us to go back to the drawing board and design every aspect of a compute system afresh, and has spawned research in every sub-area of computer science. So I have one slide in which I talk about that. So what is big data? So as such, there is no consensus as to how to define big data, but there are certain definitions which are relevant from data analytics point of view, and also from the storage management and analysis of data. So big data exceeds the reach of commonly used hardware environments and software tools to capture, manage and process it within a tolerable elapsed time for its user population. And there's another definition which is quite similar. So big data refers to data sets whose size is beyond the ability of typical database software tools to capture, store, manage and analyze. So you can see that there is commonality, exceeds the reach, beyond the ability of, right, capture, manage and process, capture, store, manage and analyze. So you can see that two definitions are in sync with each other. And so this is what is big data. And big data poses a challenge to our capabilities. So data scaling, outdoing scaling of compute resources, and CPU speed not increasing either. So so these are the challenges. So how to deal with this humongous amount of data that is there around us. And at the same time, big data offers a big opportunity. So we are able to collect so much data so that it allows us to understand a lot of things that are happening around us. So this is a list. I mean, this is just a sample. I have not enumerated everything. So it gives us an opportunity to be more and more innovative. So now these are the like big data sources. So you can see telecom is a big, telecom data is huge. Then there are like IP traffic, IP network traffic generates huge amount of data. The World Wide Web is huge. Weblog data. So you can see there are around 160 million websites, email data, satellite imaging data, social networking data, genome, and CERN's Large Hadron Collider. So it generates around 15 petabytes of data per year. So these are all sources of big data. So is it just a hype or a real challenge or a great opportunity, right? So it is basically a challenge in terms of how to manage and use this data that the mankind is generating. And it is an opportunity in terms of what we can do with this data to make our planet a better place to live, right? And we are living in a world of data, but still it is not completely data driven, but it will be in the coming years. And we are generating more data that we can handle, and using data to our benefit is a far cry. So first of all, we should worry about capturing that data and storing that data, and then only we can worry about how we can use this to our benefit. But that is what is driving all of us. So high time we figured out how to tame this monster and use it for the benefit of the society at large. So there are lots of quotes that are floating around, but some of them I like. So this comes from Dheeraj Rajaram, the founder of New Sigma, a data analytics company based out of Bangalore. So data is the new oil, and there is a growing need for the ability to refine it. So oil means, when I say oil, so it is basically that the world economy is based on oil, and many countries which are rich in oil are rich countries, right? So, but data has changed all this, and so if you have lots of data and if you have the capability to refine it, then you can make lots of money. And another interesting quote that comes from the director of research at Google: so we don't have better algorithms, we just have more data. So basically algorithms, so we need to be able to write or design algorithms that are able to scale with the increasing amounts of data. So there is a very nice article or white paper that was published, and a lot of leading researchers across the US contributed towards this, and it basically highlights the challenges and the opportunities that one can have in the area of big data, right, analytics. So it is very nicely summarized in this article. So data analysis, organization, retrieval, and modeling are the fundamental challenges. And data analysis is a clear bottleneck in many applications, both due to lack of scalability of the algorithms and due to the complexity of the data that needs to be analyzed. So complexity basically comes from the heterogeneity of data. Data comes in all shapes and sizes, right? So that makes big data a very, very challenging area. And in the next slide is basically the flow big data analysis pipeline, and at the bottom are the complexities that big data poses. So this is like, it starts like since we have almost through a course on data warehousing. So you can see acquisition, recording of data, then extraction and cleaning, and then aggregation, representation, integration, modeling, and interpretation and analysis. So this is where data warehousing would come in, right? And all this is made complex by the presence of heterogeneity of the data, scale of the data, the real-time requirements. We also are worried about privacy, and also human collaboration is required, right? So all this makes it difficult, right? So you can see, look at this article. So it is a highly recommended article for anybody who wants to do something in big data analytics. And as I said, It has spawned research in databases. So we are now talking in terms of NoSQL databases and column-oriented databases, graph databases, right, in-memory databases. So all these things are coming because of big data. And then data analytics in general, where we talk about data warehousing, and the next in continuum is data mining and machine learning. And also we talk about parallel programming and programming models, distributed and high performance computing, domain specific languages, storage technologies, algorithms and data structures. You name it and it is there. Right, and also something about green computing, because these data centers are guzzlers of power. So you need to see how you can save power in these data centers. So all this is happening. So it's a very happening time in terms of computer science and related areas. Yeah. So data warehousing, data mining and machine learning are at the core of big data analytics. So in this course, we basically focused on data warehousing. And we, like in all the data centers, there's a technology that is pervasive, and that is the cluster computing, or the cluster technology. So why cluster computing? Because it is scalable. That is the biggest strong point of cluster computing, and it is the only way forward to deal with big data. And I recommend that you embrace this technology till any new disruptive or revolutionary technology surfaces. So till that time, cluster computing is the way forward. And now this particular thing is about the extended RDBMS architecture, and what kind of things RDBMSs are doing to handle big data. So they must support new data types required by big data, like vectors and matrices, multimedia data, unstructured and semi-structured data, graph data, and collection of name-value pairs. So this is typically used in MapReduce, and it is also called as data bags. And they must also provide support for processing new data types within the RDBMS inner loop by means of user-defined functions. So this is another kind of support that is expected of RDBMSs. And as I said, so these points have been taken from the Kimball's book. So let me now turn attention towards MapReduce. So which is a kind of a framework proposed by Google. And so let me introduce this. And Hadoop is an open source, so MapReduce is kind of proprietary of Google, whereas Hadoop is an open source implementation of the same, and it is done by Apache in collaboration with Yahoo. So Yahoo has also contributed in a big way to Hadoop. So what's there in the name? So if you look at MapReduce, so everything is there in the name. So it is map plus reduce. So both functions are used in functional programming, and has primitives in Lisp and other functional programming languages. And so what is functional programming? So I'll just give you a brief overview of this, and then we'll skip that portion on Gopher, which is a simple implementation of one of the functional programming languages. And this MapReduce was proposed in 2004 by Jeffrey Dean and Sanjay Gehmawat. So functional programming is a programming paradigm that treats computation as the evaluation of mathematical functions. So it was initially proposed to evaluate mathematical functions, and it's a kind of an interactive programming language, and the basic structure is like expression and value. So you give an expression and it would return a value. So you can see here, so if I provide this function, right, and a set of arguments, So scheme, which is a dialect of Lisp, is the second oldest programming language, oldest functional programming language that is still in use. So it's taken this the syntax of scheme, and we write plus, say 12, 23, 34, 45, so it will return me the sum of these numbers, right? So the main thing here is that there's a list of arguments that you can process. So I think I'll skip this part on functional programming. So if you're interested, you can just look at this. So it basically talks about how it has evolved. So I'll just skip this. What I'll focus on is that there are some implementations of some important implementations of functional programming that I'll try to highlight. So you can see Haskell and and there's one more language in this Lisp, and it was the first functional programming language that was in use. And ML, Scheme, and adjustment to Lisp, Miranda, and Clean are other examples of functional programming languages. And Haskell, the first unified PL, and Gopher, a simplified version of Haskell. So, and Miranda. So these are some other functional programming languages. So if you are interested in that, you can take up any one of these, right? And Gopher I've chosen because it's a very simplified version, and the reference for functional programming is Fokker article on functional programming. So what I'll do is I'll skip this discussion on Gopher, right, and straight away take you to map and reduce. Right. So MapReduce and Hadoop. So what is it? So it is basically a programming model and its associated implementation, and it provides a very high level of abstraction but has limitations, and only data parallel tasks stand to benefit. So if there is anything that you want to do, any task that is data parallel, so if you want to do that, then there is nothing like Hadoop and MapReduce, right? So basically it is implemented on top of a cluster, right? So that's why I mentioned I had a brief overview of cluster, right? And the clusters, I hope all of you understand this cluster technology or cluster computing. So MapReduce and Hadoop work on top of clusters. So MapReduce does what is it provides you it basically provides you with a kind of abstraction in terms of that it hides parallel and distributed concepts from the users and programmers, and even novice users and programmers can leverage cluster computing for data intensive problems. And cluster, grid, and MapReduce are intended platforms for general purpose computing. So if I'm not going to talk about cluster and grid here, but focus on, so these are two other distributed computing paradigms, cluster and grid, right? And MapReduce is the latest one, and there are some other new developments in this area. And Hadoop, as I said, is an open source implementation of MapReduce, and Pig is a language that is a high level language built on top of Hadoop. So Pig Hadoop combination is very, very effective. So what it does is basically works by breaking processing into two phases. So one is the map phase, which is inherently parallel. So you can do the map phase in parallel, and so each list element processed independently. So it is mainly about processing a list of data elements, and the part of the list can be processed by one worker or one node, and other part of the list can go to the other node. And then there is a reduce phase, so which is typically sequential, right? So it talks about map and reduce. So everything, so all the computations that you want to do have to fall, have to be mapped to map and reduce, right? So I'll show you examples. So map function, so it applies to a list. So map, so there's a function, and then there's a list, right? So this is the standard format. So calls function for each of the lists item and returns a list of the return values. For example, if I define cube x and return xxx, right? So this is the function that I've defined here before I can use it. So map cube range 1 to 11. So I don't need to write 1 to up to like this. So I can specify it like this. So it gives me the cube of all these numbers as per the definition of cube given here. So this is how map works. Reduce function, again it applies to a list, and and you can see the basic difference between map and reduce. So it basically it is similar to the aggregate functions that we have, so which operate on a list and produces a single value as an output. So here you can see a reduce function list returns a single value constructed by calling the binary function on the first two items of the list, then on the result, and then the next item, and so on. So that's why it is typically sequential. For example, to compute the sum of numbers from 1 to 11, so I am defining first the add function, and then I'm using the add function in reduce and giving the range 1 to 11. So this gives me 66, right? So this is reduce. So all computations that can be done on the MapReduce platform have to be in terms of map and reduce. So how you define the map and reduce functions, so programming is all about that. So that's the kind of design you have to carry out. So this is how I see MapReduce. So basically, let me just clear the annotations. So it is distribute. So first you distribute the data using a distributed file system. It could be HDFS if you are using the Hadoop file system, or GFS, the Google file system. And then we have the compute phase, which is the map, which can be parallelized. And then we have the compile phase, which is basically the aggregation, and we do it using reduce. So MapReduce, it's a programming model and its associated implementation, and it is a patented software, and I've given the wiki definition.